Okay, so what I would like to talk about today is some properties on solutions of this initial value problem over there. Okay, so if k is equal to 1, well, it has some physical meaning, right? This is the Korteweg-de Vries equation, and we know that this describes the propagation of waves in a shallow water channel, right? For k greater or equal than 2 is more mathematical. And what I'm going to do today is talk about some mathematical analysis regarding solution of this problem. Okay, so the outline of my talk is a little bit what I want to do today. And so persistent properties of solution of that initial value problem. Then nice, interesting property that is the propagation of regularity of that is a nonlinear dispersive model. And I'm going to give some results, and I'm going to skip the area of the problem. Okay? So this is a joint work with Pedro from the National University of Colombia and Gustavo Ponce from University of California in Santa Barbara. Okay, so this is what I would like to do today is talk about persistent properties in some weighted space. Okay, so I consider either asymmetric weights or symmetric weights. Okay? And when I talk about the persistent property, I always mean that we have an initial value problem with some data in some space, and what we want to do is to know if the solution still remains in that space. Okay? So even in the most simple cases, if you remember in the first course on PDE, when you try to solve the initial value problem using Fourier transform and begin with the initial data in the Schwartz class. Okay? So you can use the Fourier transform, you solve, and you don't care about what happened with the solution, if they remain in that space or not. Okay? So in this case, like KdV equation, it will remain in that space. You begin in the Schwartz class, you remain there. But for instance, there is another dispersive equation called Benjamin equation, and that doesn't happen. You can solve it, right? But then, in a few moments, to be in that space, you need to have a solution identically equal to 0. Okay? So it's not obvious that if you begin in a space that is very nice, like first class, you will be there, even in the linear case. Okay, so this is one thing. The other point is propagation of regularity. What I mean by that. So if you consider initial data in that space, okay, you can begin in H1, so don't worry about doing 3/4 plus. But if you know that the initial data in some part of the line, beginning in B, right, is smoother than this 3/4 of H1, then what happened with the solution? The solution is going to be regular, moving to the left. Okay, so you begin with some restriction on the right, right? You have initial data that is in some solid space, but it's smoother in one side of the line. Then, when times evolve, the solution becomes smooth. Okay? Okay, so what about the asymmetric weights? What do we know about that? What we know about that is the following. If you consider the KdV case, as Cato did in 1983, so he observed that if he considered that space L2 with exponential in X, right? Then you can treat that equation or that linear problem, right? The linear operator there is exactly to be this in the almost the left line that operate, right? Well, if you do this computation, like, well, you have a cubic there, so you will have 3 derivatives, you are going to have second derivative, so there appears the Laplace, right? So in that space, somehow the KdV now becomes a parabolic equation. And that's what the cutoff proved, right? So you have a solution that to remain in that space, right? And it has this, like 5, this parabolic behavior. Okay? In the same regard, you can think about the following problem. So you have a result of Korteweg-de Vries, Ponce, and Vega in 2007. And they were looking for these conditions to say, to guarantee uniqueness for solutions of the KdV equation, right? So what they say is, well, you have 2 solutions, right, in a smooth space with some weight. And if you know that information, the difference in some time, and this time is equal to 0, and then in time equal to 1, they belong to that space, right? In order to be there, the only way is that they are exactly the same. Okay, so you have 2 different times, okay? The difference decay like exponential of 3/2, right? And then the only way to remain in that space is that they are exactly the same, okay? So that gives you a unique continuation principle in that case. Of course, well, before say that, there is a result where you have, instead of have x to the power 3/2, you have 9/4. But why you should have x exponential of x 3/2? Well, if you look at the linear problem, right? Now you look at the linear KdV equation, you have the nonlinearity out. You can solve it, right? Again, we use the Fourier transform, and we can write it like the convolution of that function called area function and the initial data. And what we know about the area function is that they have that decay. Okay? So what we are showing in the previous theorem is that you decay as in the linear case, okay? And it should be the best result. Okay, so if you go back to the results of Korteweg-de Vries, Vega, you see that the solution, right? You cancel one of those functions, for instance, U2. The first, one of the solutions decay like that, okay? As you expect. And of course, if you want to go from one side to the other side, the only way is from one time to other time, U1 has to be identical. Okay, so what we prove is that the result is, in fact, a sharp result. Okay? So, beginning with the KdV, so you have initial data in L2, right? With the L2 with that exponential, then you can prove that, in fact, you will remain in that space, but you see that you begin with A0 in one time, and then this coefficient is deteriorating on time. Okay? So to remain in that space, you cannot be exactly a constant. Okay? So you are decaying somehow. Okay? And what is nice is that to prove that result, you just use integration by parts, right? And energy estimates with a weighted space, with a weighted, the right weight. And you can find explicitly 80. Okay, it's not like magic, but we can compute it explicitly. Okay, you can do it also for other power of k, right? And the result will change according to the regularity that is known. Right? Okay, so again, we observe that the solution always will behave in that form, right? So going back to the proof of the theorem of Escurial-Sacchini-Ponzi-Vega, you can see that in fact the solution behaves in that form for x sufficiently large. Okay? And the results always, for different powers, the only thing that change is regarding the continuous dependence. Okay? It's just an observation. Well, you also can consider a different kind of asymmetric spaces. And those in the remark C were considered by Ginevra and Suksumi to prove the uniqueness of the solution of KDB back in 1989. Okay? But there is nothing like to prove a persistent solution in those spaces. But they were very useful to prove uniqueness at the time. And regarding the same problem for Schrödinger equation, even in the 1D case, is not known. Okay, so we don't know any condition, like say, well, in two different times, right? You have a decay like exponential, then you can guarantee the uniqueness of the solution. Okay, it's completely open. Okay, about symmetric weights, this is more natural, right? Before I was talking about the Schwartz class, and then when you introduce Sobolev spaces, when you take the Fourier transform in Sobolev spaces, you are thinking about Schwartz class again, right? Somehow, in the frequency. And then you can have now results either for forward times or backward times. And again, we go back to the result of the paper of 1983 of Docio Kato, where he considered now the initial value problem in that space, right? So you have the Sobolev class in one side, and then you have the usual weights there, right? And he put in there this condition, S is greater or equal than M, right? And there is a reason for that, and it's in red over there. Okay, so if you begin in that with initial data in CSM, you remain in that space whenever S be greater or equal than 2. Okay, so what you notice is that the operator, the linear operator associated to the KDB, commute with that operator x minus 3p to derivative in x, right? So that means that if you introduce a weight, you have to pay with two derivatives. Okay, so this is what the condition S greater or equal than M is stand for. Okay, so that is nice. So you know that if you begin in this C SM space, you remain in that space. Okay? Now, what about if you know that in some time you decay, right? And after some time you decay again, but your solution is only in L2. What can you say about the solution in between? So the only way to go from time 0, T0 to time T1, right, with decay is that U has to be regular. Okay? So you cannot going from one time to other time with decay, right, without being regular, even though you begin in L. Okay? So otherwise, you stay 0. And again, this property can be proved by integration by part using Kato smoothing effect somehow, or the argument of Kato to prove smoothing. So you can also say, well, I know how to solve it if S is greater or equal than M, right? What about if we put more decay, right? You have more decay. Well, you are not going to improve anything. So you're going to remain in the space CSS. But then some decay is losing somewhere. Okay? So what we are going to see in a few moments is that that decay can be transformed in regularity somehow. Okay? Okay, but before that, let me give you a nice application of this result, of the graph result. So now if you consider the solitary wave solution for the KDB, okay, so you have this nice second square function, right? And then you take that and you perturb by a compact function, right? What can you say about the asymptotic behavior of that perturbation? So what we can say is that that breaks up. Okay, so you have the solitary wave, you put a little bit of small perturbation, then the solution is not even in X. It doesn't decay like polynomial. Okay, so the exponential decay breaks down. Okay, so this is just a remark that you can be careful with, you have to be careful if you consider the different powers because of the different approach, right? So if you are in powers like k equal 2, 4, 5, you can use Ponce-Vega theory, right, to prove the decay. But in the case k equal 1 and 3, you are using these Bourgain spaces and you have more difficulty to deal with those problems. Okay, so let's skip this one. And I go into propagation of regularity. So I just give the statement of one theorem of Kenny-Ponce-Vega. This is not the optimal result for the initial value problem, but this is the one that we are going to use. And you have 3/4 with the initial data there. You can obtain a solution associated to the KDB equation, initial value, right? So you can see in this 1, 2, 3, 4, especially in the second one, you have this property that is called Stryker's inequality. And in that, you can have some kind of gain of regularity for the solution. Then the third one is called the smoothing effect of Kato type. And the fourth one is called the maximal function associated to the unitary group of the KDB equation. Okay, so this is the first result. So you begin with initial data in 3/4 plus, and you know that you have derivative enough for the initial data in just half a line. Then what you show is that you are going to have that regularity for the solution, okay? If you are moving to the left. And somehow, this is what you expect, right? So you have a dispersive equation, right? So they are, when time goes to infinity, you expect to smooth the solution, right? And this is what you have. And moreover, you can have this inequality. You still gain locally a little bit more derivative. Okay, so you can also combine what we did before, right? So you have now weight, initial data with some weight, right? But you begin again in 3/4, but you have some weight in the half line, the positive half line, and then you're going to have this decay again, right? You recover the decay for the whole solution in the outline. Okay. And then you combine decay with smooth, right? So now you have decay. Now you can prove the smoothness for the solution. So now you have a solution, and again, moving to the left. So you have all the properties in the right for the initial data, and to the left, you get regularity. Okay, so one interesting thing is like if you have, for instance, initial data, right? That, well, in some point, in some time, you have the solution, and in some times you have some derivatives that are not in L2. Okay? What can you say about the solution after that? Okay? In some time after that. Okay? Or before that. So what you see there is that you cannot be better, right? Before. Okay? So you, in some time t hat, the derivatives are not in L2 before you were as bad as now, right? So you cannot improve from okay? This is this is more than that, right? So what you say is you are in some time, right? You have some derivative, a number of derivative, and besides you have more than the derivative there. Okay? So from this time on, you can gain regularity. Before, you cannot be there. So if you have a singularity, right? It has to be before. So what this means is you have infinite propagation of regularity. And it has to do, this has to do with what is called the resolution of conjecture, right? So you have what you expect. What is the resolution conjecture? What you expect is that at the end, you will say something about the solution, like the solution has to be smooth, plus solitons, or enso, right? So that part that is smooth, this is a good indication of this result. Okay, so you are going to have a smooth solution in future time. Okay? But still is open to know this. Just for the way equation, you know that it's already. Okay, so before finish, let me see if I have this. Okay, no, I'm gonna give one more to finish this thing. And before I say that we can put extra decay, and we don't know if we can recover the regularity. Okay? So we can recover, but we can recover only if B is not positive, but it's just a fixed number. So you can have some regularity gain, but only in that part. Okay? So you don't gain everywhere. Right? But you can recover that decay in regularity. Basically, what we use for that result is the Stricker estimate. Okay, so again, we have the Stricker estimate is one here. And what we do is energy estimates with a weight that depend on x and t, and we use the Stricker estimate just to recover. Instead to use Sobolev, we use Stricker estimate. And this is basically what we want to say. Thank you.